My name is Jimmy and I'm from Zurich. And together with Julian and Laura that just asked a question, we developed DelGrad, which is an exact method, a method for computing exact event-based gradients in spiking networks for training both delays and weights. So usually when we are training a spiking net, we get input from an event-based sensor, let's say an event-based camera. And what people are usually doing is that they're taking these events and time binning them into a binary vector representing the amplitude of the spikes. Then they are accumulating those spikes, weighting them, accumulating, and eventually passing through a LIF dynamic, creating an output spike. Also represented through the amplitude of the spike by a binary vector. Now, on the other side, you have like event-based framework where you conserve the asynchronicity of your events by representing your information, the input spikes, through their timing. Again, you are weighting the spikes, going through an activation function, and eventually you get an output spike time. There are several advantages of having an event-based framework. First, you are exact at the forward pass, right? Because if you are doing time binning, eventually you are making some approximation. In gray here, you have the exact dynamic, while the dots here represent the time step version. Second, you are precise at backward pass. Because here you have a discrete input that goes into a discrete output, your activation function is non-differentiable. And therefore, we are using most of the time surrogate gradients that introduce additional approximation. While on this side, in the event-based framework, as we are going from continuous input to continuous output, the activation function is smoother and then therefore can be differentiable. So as it's differentiable, then you don't have the approximation coming from the surrogate gradient. Again, here you have another advantages because as the complexity of your algorithm is scaling with the size of the input. And here the input is the number of spikes. While on this one, the complexity of your algorithm is scaling with the number of time step or the precision of the time. If you're not smart about it, because I know that people have some about that. After, if we look at the number of observables for training a neural network, here what you need to compute your gradients is the membrane voltage at every time step. While in this case, you only require the output spike timing to compute your gradients, which is way more hardware friendly because in your hardware, then you would have to record your membrane voltage at every time step. While in this one, you would just have to record the output spike timing, which is a great advantage in terms of I/O bandwidth because you need way less information that goes out of your hardware for training in the loop. And finally, if we want to train delays with that, and that's why I'm in the delay session. So on this side, right, not only training the synaptic weight, but also the synaptic delays, then you are adding a delay here to your indexes. So you are shifting every of your input by a delay. Eventually, to compute the gradients through the chain rule, you'll get at some point to have the differentiation from an index to the delays. And doing the derivative of an index is not possible. While on this other side, you just have a simple addition. And through the chain rule, you know that the derivative on an addition is very trivial. Now let's look at the results. So we assessed our method on the yin-yang dataset that Gabriel just presented, which consists in classifying whether a dot belongs to yin or yang or the green part and encoded in a time to first spike encoding. Regarding the results, we got that delay-based network are always outperforming weight-only based network, and that independently of the size of the neural network. We also validate that observation for normalized in terms of number of parameters. As I said, it's a hardware-friendly method, so we were able to train this delay-based network on the Brainscale's 2 neuromorphic chip, and we again made the observation that weight only are less performant than delay-based network for both ideal hardware-aware and hardware emulation. And finally, if we contextualize our method in the state of the art, you can see that this work is better in terms of test error for a reduced number of hidden neurons. Thank you.